Hello, how's everybody doing? Today we will investigate the experiment number 12 in Labflow, which is measuring Avogadro's number. I will give you a quick overview of the experiment, and then I will share my Excel page to show you how to do the calculations. In this experiment, we will determine the Avogadro's number, which is the number of particles in 1 mole of substance. And we will use an electrochemical method. We will apply a current to a metal circuit, causing the metal to dissolve as ions and lose electrons. In our experiment, the Avogadro number is the number of electrons in 1 mole of electrons. So we need to determine both the number of electrons and the mole of electrons. And the Avogadro number is the total number of electrons divided by the number of moles of electrons. And we will determine the Avogadro's number when a piece of copper is placed in a solution of sodium sulfate. Let me share the whiteboard so you can see the experiment that we are doing today. You will have a beaker. Filled with DI water and sodium sulfate, and then you will have a piece of copper metal, another piece of copper metal, and this will be connected to an electrical power supply. This is the positive, this is the negative, and we are going to have an amp meter here to measure the current. So here we can vary the current. We can vary the power supply, and we can measure the current. So this is copper. It can be copper or zinc, but we will use 2 pieces of copper. So we will place this copper, and this copper is connected to the positive. This is to the, let me change to the red end, to the red terminal of the power supply, and that is the positive end. And we will apply an electrical current. This is electrolysis. I'm just trying to give you an idea of what is the process. So when you then have to calculate and look at the data, you know what is the experiment about. So the metal, the copper is connected to the positive end. Very good. When we apply an electrical current, what is going to happen in this copper that is connected to the positive end? What happened is that the copper is going to dissolve copper +2 + 2 electrons. So in solution, we are going to have copper plus 2 that comes from the positive electrode. And the electrons are going to be that way. And here, the electrons are coming in this way. And this is the anode. Don't confuse with the batteries. This is an electrolysis. We are forcing this copper to dissolve using an electrical current. So this is what is happening in the anode. So the metal or the copper that is connected to the positive end, before we apply any current, we are going to take the weight, the mass of that piece of copper. Then we will apply a current for about 5 minutes, dry it again, and take the mass again. We record the weight loss of this metal that is connected to the positive end. We repeat this process for 5 times. So when you look at the data, you will see the weight loss of the copper, and you know that each time you are dissolving the metal and you are recording that weight loss, the weight loss of the copper that is attached to the positive terminal. And then what do we need to do? Then we will use Excel. We will use Excel. I will show you shortly how to do the calculations. And we calculate and plot the data of the cumulative number of electrons and moles of electrons after each time interval. So the x-axis is the number of moles. Number of moles of electrons. Very good. This is a quick overview, so you know the general idea. And then the y-axis is the number of electrons. And when we do that, we are going to have some points, and we are going to have a line like that. And the slope of this line is equal to the Avogadro number. Why is that? Because we said the Avogadro number is the number of moles per moles of electrons. So if we calculate the number of moles of electrons and the number of electrons, then we do that graph, we take the slope, and that will be our Avogadro's number. But how are we calculating? We need to know how to calculate both the number of electrons and the moles of electrons. Let's start with the number of moles of electrons. That is easy. How do we calculate the number of moles of electrons? From the number of moles of the metal dissolved. Each mole of copper that is dissolved provides 2 moles of electrons right here. The copper, elemental copper, oxidizes to copper plus 2 and releases 2 moles of electrons. So if we know the mass of copper dissolved, then we know the moles of copper dissolved just by dividing the mass by the atomic weight. So that won't be a problem. And then all we have to do is multiply that value by 2 to find the number of moles of electrons released. Does it make sense? If we know how the mass of copper that is lost, we convert it into moles of copper using the atomic weight. And then, because the molar ratio, 1 mole of copper releases 2 moles of electrons, we just multiply by 2. So we are going to obtain the number of moles of electrons that way, using the weight of the mass, the weight loss of the mass of copper. How are we calculating the total number of electrons that is involved in this process? That will be done by measuring the current and the time. So we are going, you don't see here very well, but we are going to have a device that will allow us to measure the current, and we will measure the time. So by measuring the current and time, we know how much charge in coulombs passed through the circuit. For example, if we have a current of let's take another color. Let's say we have a current of 2.5 amps. And that current passed through the circuit for 5 minutes. 5 minutes. So we will measure the time and we will measure the current. And I will ask you, what is the total charge? The total electrical charge. And we know that the total electrical charge is going to be the current times multiplied by the time. The current, before I continue, you know that the coulomb is the fundamental unit of charge, and the amp is the unit that is used for electrical current. And it's an electrical current, 1 amp is the electrical current of 1 coulomb per second. So that means that if I have 2.5 amps equals 2.5 coulombs per second. And because I have the time in minutes, I have to convert it into seconds. That will be 1 minute is 60 seconds, so 300 seconds. This cancels, and I obtain that the total charge is 750 coulombs. This is just an example. So the electrical charge is 750. So by measuring the time and the current, we can calculate the electrical charge. But we are not interested in the electrical charge. We are interested in the number of electrons. But since we know the value of the charge of 1 electron, this is given. The charge of 1 electron is a fixed number, 1.602 times 10 raised to the minus 19 coulombs. And this is the charge of 1 electron. So that means that if I divide and change the color, the number of electrons is going to be the total, the electrical charge that we just calculated, divided by the charge. One electron has a charge, this is data that is given, one electron has a charge of 1.602 times 10 raised to the minus 19 coulombs. And that is how I calculate the number of electrons that I will need that data when I go to Excel for my y-axis. In this case, I obtain 4.68 times 10 to the 21st electrons. And that's how I'm going to calculate the number of electrons using the current. So first, I multiply the current by the time, and then I divide by the charge of one electron. So this is the general idea. The x-axis is going to be the number of moles of electrons, and the y-axis is going to be the number of electrons. And the slope of that line is equal to the Avogadro's number. Very good. So now that we understand the experiment and how we are calculating the number of electrons, the number of moles of electrons, let's look at the details in the Excel sheet. And I want to show you how you have to prepare your Excel sheet to complete your report and to calculate the Avogadro's number. And before I go to the Excel sheet, I want to show you that you will have to use your data. So when you go to Labflow, you will have to look at the sample data. That is the raw data that you will have to bring to the Excel sheet. So pay attention, everyone will have a different data. But what are they giving us? The step 0, the step number 0. This is the metal before any current has passed through. So we start with this mass of copper. And then what happens? Step 1, we applied 300 seconds of the current, that is 0.5 amps. And the weight, we lost weight. In the step number 1, the weight went from 35.9191 to 35.940. So what is the weight loss for step 1? The change in the weight is going to be 35.991 minus 35.940. So we are going to use the mass, the current, 0.5. We will need the atomic mass of copper. We can use that. And we will need this time interval. So now that you are going to bring all that data to the Excel sheet, I want to share my Excel sheet. Very good. I hope everybody can see this page. Let me see if you can see my Excel sheet. Looks like not for some reason. Let me try one more time. Okay, now we are sharing. Very good. So you can see my Excel sheet. So you will have to start, and you will have to start preparing a table like this. Let's erase this, so we will do it together. And let's erase all this. We will do it together. And the raw data is on the left. So prepare a spreadsheet when you start, similar to mine. So column A is the step. So write step. Column B, runtime. Column C, the mass. And column D, the charge in coulombs. So that is the raw data. The steps, we've just seen it in the sample data. Column B, the runtime, as I showed you before. The mass is given. Each step, how much mass was lost. And the charge of the coulomb, this is just what we have to do in this one is basically we are multiplying. Remember I said that we have to multiply the average current, that is 0.5 amps, by the time. So if we look at the formula here, it says equal 0.5, that is the average current, times B5, that is the time. Obviously, the step 0, all the entries in this row 5 for me, or the step 0, are for the metal strip before any current has passed through. But then, in step 1, is basically multiplying this column B by 0.5. Is the runtime multiplied by 0.5. When I click here, you will see the formula. Basically, what I do, let's erase it. So how you calculate it, you do equal 0.5, then to multiply, we do shift and then the number 8. That little thing is the symbol that we use for multiplication. And then we have to multiply by the time. And then enter. And I don't have to do it for all of them. I just look at this little cross. I extend it and down, and Excel is doing it for me. So this is the first part that we have to do in Excel. Just prepare a table similar to mine and bring the raw data from the sample data. Very good. Now we have to go to the calculations. Basically, we said that we need to calculate the moles of the electrons and the number of electrons. And we said that the moles of electrons are going to be calculated from the mass change. So here it comes. One important thing, please note that the mass changes, the total times, and all the associated values are cumulative. Please remember that. So we will compare each value in the step 2, 3, 4, 5 to the start, to the step number 0, instead of comparing with individual step, because we are drawing a graph. So all the values have to be cumulative. Very good. So now we are in column F. We have to calculate the mass change. So we want to know how much mass is lost from step 0. So what do we need to know? What do we need to do? Let's say we are here. We didn't lose anything, right? Because we didn't pass any current in step number 0. So basically, it will be 0. It will be no mass change. I started with 35.990 and I ended up with the same. But now I have to compare all the rest, C6, C7, C8, C9, C10, to the first one, to C5. So let's say I'm calculating the mass change for F6. What is the calculations that I need to do? Obviously, it's 35.991 minus 35.940. But I want Excel to do it. So how I'm going to do it? I will do equal what? Because we are comparing always to the step 0, I need to log that step. So I will write C, the dollar number, and then 5. That means I always want to compare to the step number 0. Minus, in this case, I just need this. Very good. And because I want Excel to do it for me, again, I'll do that. And Excel is doing it all the time. And because I wrote C, the dollar sign, and 5, each time, for example, for this case, 0.1 is doing 3.891 minus is always doing 3.991 minus the other. In this case, for example, to obtain the F8 is 3.991 minus 3.840. Very good. So this is how we calculate the mass change. You can do it with a calculator. You can do, for example, the mass in step 0 minus the mass in step 1. Then for the next one, mass in step 0 minus mass in step 2. But Excel will help you to do it much faster. To complete the column G, how are we doing the column G, the moles of copper? We know the mass change, but we want to know it in the moles. So we just need to divide the mass change in column F by the atomic mass of copper that is given. We have many options. You can just write the number, or you can do again the same thing, equal this mass divided by H $1. Enter. Obviously, it's going to be 0, but I already have the formula for all the rest. If you want, here I said H10 because I wrote here the atomic weight of the copper. You can divide by the number and you're going to obtain the same thing. And now that we have the moles of copper, we are going to column H. We need to complete the moles of electrons. We just need to multiply, as we saw before, the moles of the metal by 2. Remember that equation. 1 copper gives you an ion, copper plus 2, plus 2 electrons. So each mole of copper will give you 2 moles of electrons. So all we have to do is multiply by 2. So what we do is equal the previous cell and then multiply by 2. Very good. And then again, Excel is doing it for me. Isn't that good? Now we have to calculate the next column, the total coulombs. How do we do that? Pay attention. We add the coulombs from the previous step. For example, in this case, obviously, we didn't add any current, so it's going to be 0. But let's say I want to know the total coulombs here. It's going to be equal the previous cell, because I'm doing the cumulative, the previous cell plus the coulombs that from that step. You know what I'm doing? This is a charge. I'm calculating the total charge, the cumulative. In this case, it's 150 plus 0. Very good. And then we do it cumulative, and we obtain the total coulombs. And we are very, very close, because how did we say we complete the number of electrons? We said that we divide the number of coulombs, which is this column, by the charge of 1 electron. And I enter that in this cell. You can write the number, or you can do it in a different way. For example, this one is going to be 0. Very good. So how can we do it? We can do it this way. Equal this charge divided by, I can do D and then the dollar sign and then 1, which is, and then, or I can just write the charge of 1 electron. And that is how I calculate the number of electrons. So all I've done is divide the total coulombs by 1.6 times 10 raised to the minus 19. And that's how I obtain the number of electrons. But I need to have the total coulombs first. Very good. And now we are ready to plot the data. Remember, the x-axis is the moles of electrons, the H column. Very good. And the y-axis is the number of electrons. So now we calculated, Excel calculated the data for us, and now we are going to graph this. How are we going to graph? Remember, you did some other. You go to Insert. Very good. Then, what do? Insert, And then you pick, which chart do you pick? Remember, the scatter. This is very important. We don't want the dots to be connected. Now that you have that empty box, you click on select data, you click on add data, series name. Well, the series name will be the name of the graph, so you can write Avogadro's number. Very good. Now we click on the series X and we highlight the X, the column of the values. But remember, it specifically say don't include the 0. So we only want the values that we measure. So when you highlight, don't highlight the 0. Very good. Now we are going to do the same for the Y. That is the number of electrons. So I highlight that data and I say OK. And I say OK. So you are going to obtain this graph. Very good. Let me see if you can see, if I put it down there. Okay, I think you can see. Very good. Now, you have the graph, but a graph, if it doesn't have units, it doesn't have name of the axis, you don't know what that is. So we say add chart element. And we want to add axis titles. Let's start with the horizontal. What are we going to write in the horizontal? Moles of electrons. And the units is going to be moles. Very good. Now we go again, add chart element, titles, but we go to the primary vertical. So what is the name of that? It's the number of electrons. We don't have units for that. Now what else we want? We probably want grid lines, minor horizontal. We probably want grid lines, minor vertical. And now what else we need to add to this graph? We need to add a trend line because we see the line, but we need the equation. If we don't have the equation, we don't know the Avogadro number. We need the slope. How do we add a trend line? Here, trend line. Make sure you pick linear. This is the best fit. And this is how you have the trend line. But still, we need the equation. So what do? Here, trend line. Go down here, more trend line options. Click on there. On the right, you will see, scroll down, that you need to display. Click on display equation on chart and click on the R. And then you have in the graph, you have the equation. So look at the equation. What is the Avogadro's number? The Avogadro number is the slope. In this case, is 6 raised to the 23rd power. But one important thing, the values displayed when you do this should be in scientific notation. But the default, when you will do it, the default setting, set the display to 1 sig fig. So click on that box, right click, on the box and select Format Trendline Label. And then in the menu, select, when it says Category, select Scientific. Here, this is important. And then decimal places, you can say 2. And then you close. Very good. See how different it is? So don't forget to do that. Right-click on the box and change it in the category to scientific. That will give you a better value. And then we have the R-squared value. That is the statistical correlation coefficient for the line. So you know that it's indicating us how good is the data fitting in the line. Look how good is our number. It says 1. If R-squared is less than 0.95, we're going to say, oh, we might have serious problems with the data. But we have excellent data. And the units, what are the units? You know, we are doing number of electrons that has no units divided by moles of electrons. The units are then moles raised to the -1 per mole. Very good. So now we know how to do it, how to calculate the Avogadro number in Excel, and the Avogadro number is the slope. So let me share here now. You have the y-intercept, that is this number, 1.5 times 10 raised to the 19th power, and you have 5.87 raised times 10 raised to the 23rd. That is your Avogadro number. Very good. So I think this is the main thing to calculate the Avogadro number. And then once you complete this, there are just a few more questions. Let me share now the page of the experiment. Okay, so you will have a page like that. You will have your spreadsheet with what we just did. Then you will have to write the slope that we just did, the y-intercept, that is what we just did, the R-squared, you bring it here, we just did. Obviously, what is your experimental value? Obviously, your experimental value is the slope, so it's going to be exactly the same. And then the percent error. They are asking you to calculate the percent error. So what is the formula of the percent error? The percent error is going to be the observed value minus the accepted value divided by the accepted value times 100. So in our case, what is the true value or the accepted value for the Avogadro number? That is the one that you always use. 6.022 times 10 to the 23rd to 1 per mole. And this same number goes here and goes here. This is the accepted value. And what is the observed value? The observed value is the one that we calculated. And then you multiply by 100, and that's how you are going to calculate your percent error. And here is what we talk. They are telling you if your R is higher or equal to 0.999 is excellent. So they will ask you, depending on the value that you obtain for R square, to tell how good basically is your fit of your data, how well your data fits in the linear regression. And then how does we are about to complete, and then you have what if questions. What if questions? Those questions, you have to be specific when you answer those questions. Because it's when you explain, many students say it or this, and it's not clear. So you need to be specific in your answer. Either you say the experimental value is higher than the true value, or you say the true value is higher than the experimental value. The observed value or the experimental value is the value that you calculated with numbers that you collected. And the true value is the one that we accept. So for example, let's look at this. It says the balance you used for weighting the metal strip does not zero properly. And consequently, all your mass measurements are high by precisely 0.050 grams. What effect would this have on your experimental value of the Avogadro number? Think about it. When do you use the mass? Do you use the absolute mass or you use the mass change? Do you think it's going to change the Avogadro's number value? In this case, the error of one measurement is cancelled out by the second measurement because you are not using the absolute value. So the mass change is not going to be affected. And then the moles of copper are not going to be affected. And then the moles of electrons are not going to be affected. So the Avogadro number is not going to be affected. And what happened with the next question? Look at B. It says the electrical leads from the constant current system are damaged slightly, leading to a small short circuit that results in 10% of the measured current passing through the short circuit without going through the metal strips. So the current displayed is the total current, but only 90% of this current leads to dissolution of the metal. And they ask, what effect would this have on your experimental value of the Avogadro number? And they help us. They say, note that you complete your calculations assuming that 100% of the current is applied to dissolving the metal strip. So you read the 100%, but only 90% of the current displayed leads to the dissolution of the metal. So the experimental value of the current is higher than the true value. Think about it. We read 100%, that is the experimental value of the current, is higher than the true value. The true value is 90%. And then the experimental value of the number of electrons is higher than the true value. If the current is higher, the number of electrons is higher. And then because the Avogadro number is the number of electrons divided by the moles of electrons, so the number of electrons is in the numerator, and it has a higher number, what are we concluding? That the experimental value of Avogadro's number is higher than the true value. Think about it, and you will see that you have to be specific when you explain saying true value and experimental value. And then it will be clear for everybody to understand what you mean. And this will conclude the workshop of today. And I want to thank everybody for listening to me and looking forward to seeing you next time. Thank you.